Any general questions or problems? Yeah. I sometimes refer to these problems as chemical soup just because it's a whole bunch of chemicals mixed together. And as we add more reaction types going forward, since we'll soon be leaving acids and bases behind, we could make it even soupier, and maybe we will. Right? But I promise you a problem, and here it is. So I mix together, in this case, three things, right? Sodium iodate, sodium hydroxide, and iodic acid. And I ask the usual acid-base question, which is what is the pH of the mixture? Again, as we add other reaction types, there might be other things going on, but for now, still pH. And so, take a few minutes, solve it, and then we'll talk about it. You may need to write it down because I really want to show you these instead of this. So take a couple minutes and write it down, and then I will throw up the Ka and Kb values. Feel free to talk to the people around you, chat with the people not around you, but on the Zoom with you. Just so we don't get too far astray, what's the first thing I want to do here? Ms. Al says, dissociate the salt. I would say that's the second thing I want to do, because the first thing I need to do is to do what? Third thing I want to do, he said identify the acids and bases. First thing I need to do is identify what's what. What is sodium iodate? What kind of compound? It's a salt. Once I've identified it's a salt, I might want to dissociate. What is sodium hydroxide? Oops. What is sodium hydroxide? It's a base. Not only is it a base, it's a strong base, and not only is it a strong base, it's also a salt. And HiO3, also known as iodic acid. What kind of compound is it? It's an acid. Right, so again, my first task has to be identify them, right? Because I don't know to dissociate the salt until I know it's a salt. Once I've identified them, the salts get dissociated, right? So sodium iodate is a salt. So it is not sodium iodate when in solution, it's sodium and iodate. Sodium hydroxide is a salt, so technically it's not sodium hydroxide when it's in a solution, it's sodium and hydroxide, right? At this point, once I've identified everything and dissociated everything, now it's time identify the acids and bases, right? In addition to this, I've got HiO3, and of course, I also have water. So HiO3, what is it? Acid still. Iodate, base. Hydroxide, base. Sodium, technically an acid. And water, both an acid and a base. So technically, I have 3 acids and 3 bases. At this point, what do I want to do? React each acid with each base. I turn you back to your previously scheduled. Okay, checking back in. All right, again, I have 3 acids and 3 bases. That means technically I have how many acid-base reactions? 9, right? And so again, it's every acid with every base. So iodic acid with all 3 bases, water with all 3 bases, and again, technically sodium with all 3 bases. Of course, I can simplify my life somewhat if I recognize what? Sodium's a spectator, and the reason it's a spectator is it's a conjugate acid of a strong base, which essentially makes its Ka 0, right? And so, I mean, at least approaching 0, if not exactly 0. And so, technically speaking, right, all of these reactions, because of the sodium, are all essentially going to have a K that's approximately 0. So, you know, I could calculate them, or I can recognize that sodium is a classic spectator because its Ka is effectively 0. And that gets me down to 6 reactions. At this point, what do I want to do? Well, find all the Ks, right? Because again, I'm going to solve them biggest K to smallest K, right? And again, some of these I know virtually off the top of my head. Others I might have to calculate. Which ones do we know right off the bat? Feel free to play on the chat. I'm looking at it. Which ones do I know? KW from in the room. So this is 10 to the minus 14. Anthony says HiO3. I have 3 HiO3s. Which one are you referring to? I assume I know, but the one with water, which is just a Ka, which I think was 1.7 times 10 to the minus 4 for my table. I can't make ice charts until I know which one goes first, right? There's only one more that might be semi-obvious, not requiring any calculation. Yeah, I mean, again, this is a conjugate with its conjugate. So technically its K is 1. There's one other similar one. Yeah, I mean, this again, same issue. I mean, neither one of these will change the concentration of anything because the products are the same as the reactants. And so that only leaves me 2 that I have to figure out, right? And so iodate with water, what kind of reaction is this? It's a Kb. Specifically, it's a Kb of a conjugate, so how do I get the K? Thank you, Kw over Ka. And then up top, what kind of reaction is that? Yeah, that's technically a K neutralization reaction. How do I get the K of that? Yeah, the K of the acid times the Kb of the base over Kw. Right. So since the hydroxide, again, is my sodium hydroxide, which is strong, essentially that top one ends up being super freaking big. The Ka, as we said, was 1.7 times 10 to the minus 4, right? These two essentially don't do anything. I mean, even though they technically have fairly large Ks, all things considered, they don't change the concentration of anything, right? And then bringing up the rear, our good old Kw, which is, again, almost always last. And once again, no disappointment here. At 10 to the minus 14, it's last, right? The iodate reaction is slightly above that, right? At 10 to the minus 11. And so I have a relatively clear ranking of what is now only 4 reactions I could possibly care about. Right. These two are at the back end, and up front, right, I essentially have one super freaking big one and then one weak acid equilibrium. And so biggest K first, right? I did mix 3 solutions together. And as I'm fond of saying, if you mix 2 solutions, you dilute them both. The corollary to that is if you mix 3 solutions, you dilute all 3 of them. So technically, right, if I want to do this in molarity, which I could also play around with moles for a while if I want, but in the end, if I get to a K equation, it has to be molarity. So, all right, the HiO3, there's 10 mils of 0.1 mil, which is diluted to a total volume of 110 milliliters. For the hydroxide, which came from the sodium hydroxide, there's 50 mils of 0.1 molar diluted to 110 milliliters. And then similarly, the iodate, which came from the sodium iodate, is similarly 50 milliliters of 0.1 molar diluted to 110 milliliters total. Right. At this point, it's as many ice charts and K equations as it takes to get the pH. Right. And there's no question as to which one was largest, since there was only one super friggin' big one. How am I going to solve it? Maybe I should change the question. How are you going to solve it? And the answer can't be wait for me to solve it. Well, I suppose the answer could be wait for me to solve it. since K is super freaking big, right, the implication of being super freaking big is that you're really not in equilibrium, right? And so in a phrase, you are a limiting reactant problem, which means what in terms of my ice chart? The what? Could we be more specific which one? Yeah, the HiO3, since there's less of it, has to be the limiting reagent, right? Which actually allows me to solve the whole ice chart. Since X must be 0.009091 to no particular number of sig figs. And I'm done. And now, what do I do next? Go to the next biggest K, which is it'd be what? I can't hear you. The Ka of I, or the which one? Oh, the Kb for the IO3 minus, because technically the second biggest K, if I ignore these, which again don't change anything, right? Technically the second biggest K is this, but I don't have any HiO3, right? Again, as a general rule, when I have freaking bigger reactions, which are essentially limiting reactant problems, I'm running out of stuff, which means I also no longer can do any reaction which involves said stuff. So in this case, since the HiO3 was the limiting reagent, there is no HiO3. So technically, even though the second biggest reaction, right, was that, I can't do it anymore. And so I'm actually down to my two little reactions, right? The Kb of iodate, right, is 10 to the minus 11, and then there's good old Kw at the back end if I care. So again, second reaction always starts where the first one ended. So at this point, I have no iodic acid. I have 0.05454 molar iodate. I do have hydroxide still left over from the first reaction. And so I just start the second one where the first one ended. Minus x, plus x, and plus x, I plus c equals E. All right. In this case, I know the K. Can't hurt to assume K, or excuse me, X. I don't know why there's a 0.0125 there. So much for my copy and paste. If I assume X is less than 0.03636, both of these X's should be insignificant. And if I do the math, what I tend to phrase is triply good news, right? X is small. So that validates my treating these as separate reactions. It also means I don't have to do any fancy algebra here. Right. It also means I'm all but done because things stop changing. I would be completely done if I had any hydronium at this point, but I don't. Right. All I have is hydroxide, which is always true if I have a basic solution, but, right, I do get hydronium from the KW. So technically, right, I have to do that fourth reaction. Right. Of course, I can also shorthand it since I know the solution to my KW at room temperature is pH plus POH equals 14. Right. But that is technically, right, what happens when I solve the ice chart for the KW reaction. Effectively, that method always works. No matter how many acids and bases I have, I don't have to think much about it other than identifying the acid, bases, and salts and dissociating the salts. All right. I am not left trying to decide whether it's a buffer or an acidic solution or a basic solution. It is whatever it is based on what happens once my ice charts start resolving themselves. And in fact, up front, this might have looked like it was a buffer. After all, it had iodic acid and sodium iodate. Right. But because of the sodium hydroxide, which actually wiped out all my iodic acid, it is not, in fact, a buffer solution. It's just a strong base. It's effectively a sodium hydroxide solution where I neutralized, dare I use that word, some of the sodium hydroxide with the iodic acid. But again, I don't have to care. Right. The only time I really might want to care, buffer or not buffer, right, is if I'm going to use Henderson-Hasselbalch, and that is not a global solution to anything. It's a solution to a specific ice chart. You know, so if I get an ice chart where I have, you know, initial concentrations of the conjugates, that's my signature that it's a buffer ice chart, and that's when I would use Henderson-Hasselbalch. I don't prejudge it. I don't do a lot of thinking and figuring up front. Right. I just take it as it comes. And in the end, every acid reacts with every base in essentially a binary reaction with a single proton transfer. And I solve them biggest K to smallest k just because the bigger changes will be in the bigger Ks. Right. But technically, they all have to get to equilibrium. because they're all bumping into each other and the reaction's going to happen. Yes, no, maybe. Starting next week, a week from today, because there's no Wednesday. I mean, there is a Wednesday, but not for us. Friday, we'll talk titrations, which is really my favorite way to wrap up acids and bases. And then next week, we'll start talking about KSP reactions, which is a different aqueous reaction type. And, you know, it adds another possible set of reactions to my soup, right? But again, in all cases, I don't have to really prejudge the soup, right? If I identify the compounds, right, as acids and bases, all I've got is a whole bunch of acid-base reactions. As you'll see with KSP, those are ion-to-ion reactions. And so if I've got ions, I've also got possibly KSP reactions, which just makes my soup richer. In the end, it'll just be two different types of reactions, right? But it's still biggest K first, whether they're all acid-base reactions or some combination of different types of reactions. They all have to reach equilibrium, and the most effective way to get them all to equilibrium is do the biggest K first, because that ends up being the reaction that dominates the changes in the beaker. To Quinn's question in the chat, did your colleagues effectively address that? Other questions, problems? I give you a free 5 minutes to add to your recharge day. If you have questions on the project, please track me down today. I am undecided as to whether I'm going to have night office hours tomorrow, because God forbid everybody trying to finish the project at the last minute. Happy Monday. Try to get out in the sun a little bit. It's supposed to be nice yet again today.